Okay. So we're going to focus on yesterday we did a problem like this, right? Where we had our ceiling, right? And we had our a pulley, right? And we had
it's cool. I know, but they're like, oh, it's called a pulley. Like, hey, when you drop that pulley thing, yeah. Oh, yeah.
Because you have to pull. You have to pull.
I know, but like, it would be like scissors, like cutty. Cutters, yeah.
Cutters. Okay, so yesterday, guys, we were working on this type of problem here, right? Where, can you close that door? I'm sorry. Where we had the weight. You're late. But your stuff being here doesn't mean that you're here. I'm just trying to, guys. I just want to make sure you're on. You can be on top of stuff. The weight is pulling down. Hey, I'm not going to catch up. All right. The weight is pulling down, and the guy is pulling to kick the weight up. What did we learn yesterday in this scenario? How much was the guy having to pull on the rope to keep the weight from moving? No, just conceptually. There are no numbers here. If I'm pulling, okay, you got to stop making noise. Hannah.
I'm just trying to open this. Why is this such a big deal?
Because it's a lot of distraction. Okay, so how much conceptually did the guy have to pull down to keep the weight from moving? Did we learn yesterday?
The weight of the box.
Beautiful. The same as the weight of the box. Because there's a force that he's pulling on the rope, and that causes what in the rope? What do we call that? Tension. And the tension anywhere within the rope is the same tension. Does that make sense? Okay. What did we say was the force that we had to pull up on the pulley in this scenario? This force here, that the ceiling had to hold the pulley up, what was that equal to? Not number. Where did you get double from?
How much he's pulling in the box.
Okay. How much he's pulling in the box. Very good. Does that make sense to everybody? Right? We're there. Okay. I'm going to do a new problem. It's going to look similar, but it's going to be different. It's going to be, there's a key difference. New problem today. Here's my pulley. Okay. Here's my box. Oops.
I understand. I understand.
You don't understand the.
Why would you?
Okay, we'll talk about it. Okay. Let me even clarify it even more. Let's make a change.
No, like what's the context?
I can't hear you.
But what's the context?
Okay. I'm gonna clarify a little more.
Okay.
Yeah, he's pulling up. Okay. The box. Okay, the box is hung from the pulley. The box is hanging from the pulley.
Oh, is it pulling the pulley up?
So he's pulling the rope, which is pulling the pulley up.
Yeah, so he's like going like this.
So the idea is that you've got the pulley.
Yeah. He's pulling the box up. Isn't that the same as just pulling the box? I'm sorry.
No, well, we're gonna find out. We're gonna find out.
Wait, can I guess the idea?
Okay.
Is the idea that the left side is holding some of the weight of the box?
Well, we're gonna talk about that. So the issue is that my ropes are coming up here, but the weight is being pulled down. Versus, I was holding the weight this direction, or the weight off of that one. Does that make sense? See the difference? Okay. And it's going to change the problem. It's going to change the problem. In this case, how much was he pulling to keep the box up? The weight of the box, right? And here the pulley is having to pull up how much? Double, or the weight of the box plus whatever he's pulling, okay? All right, I'm going to delete this. Delete, and I'm going to move this over. Let's assume that we have 10 kilogram mass at the end of this pulley. Assume the pulley is weightless, okay? In order to figure this out, what I want to know is I want to know how much he has to pull up to keep the box from moving. Okay, does that make sense? Okay. Still. Or at a constant velocity. Either is the same.
Okay, I got you. So he doesn't want the box to move at all.
He's holding the box still. Or he's moving it up at a constant velocity. Each are the same amount of force. Right? Because the acceleration is 0. Right? Okay. So, in this case, I've got the weight hanging from the pulley and the cord. What's the force inside the cord called? What do we call it? Inside the rope, tension. So there's a tension in the rope here on this side of the rope. What's the tension over here on this side of the rope? If I call the tension T, the same, right? Yeah. So the tension over here is the same. So how much must he be pulling? How much must he be pulling? T. Right, let's do the free body diagram. I'm going to do the free body diagram around the thing that I'm looking for and the thing that I know. So free body diagram 1, okay, means I've got my hand and I'm going to pull up the force of the man. And what's the other force on him, on his hand?
Or the tension.
The tension from the rope pulling down, right? Everyone see that?
Mm-hmm.
And if I do my sum of the forces in the y, and assuming his hand is not moving or at a constant velocity, the net force on his hand is what? 0. Therefore, that 0 must equal the summation of what two things? Fm plus t. So in this case, Fm must equal, because t is negative in this case, right? Fm must equal t. Right, it's really
What is that then? Oh, right.
right, because Fm, no, yes?
No, wouldn't it be 0 be negative? It's to be like the opposite. Because if t is negative, then it has to be positive.
Right, so I'm saying, in this case, Fm is a positive number, t is a negative number, so Fm, because it's plus a negative, so Fm must equal t.
So Fm equals negative t. I don't get it.
Fm plus negative t equals 0.
But how does it? Why can't
This is-
why can't it just be Fm plus minus t?
You can. Well, you can do that, but the problem is, I want to make sure you guys all know it's a summation, okay? This is, in fact, a negative number, so it's really a negative t, yes, right? Because it's negative value. But I'm trying to do this with variables and not numbers at the moment. So when I bring it over, Fm equals t. Okay, so the amount of force he's pulling up is equal to the amount of tension he's pulling down.
Oh, I see.
You see what I'm saying? Okay, sorry, I didn't mean to confuse you with that. Okay, then I'm going to draw, where could I draw another free body diagram? This is really important because the boundary box of the free body diagram, where you draw, that's really important. Around the pulley. You always want to draw a free body diagram around either things you can figure out or things you know. Okay? You don't want to cut the free body diagram in the middle of the weight. You don't want to do that because you don't know what the forces are inside the weight. That's a whole separate gig. Okay? So if I do it like this, okay? I'm not going to include the weight. Now you could do it that way if you wanted to. But the key here is if I look at this, right? The amount that this bracket is pulling up is equal to the F of G of the weight of the object, right? So I'm making some assumptions.
You're still using it.
I'm still using it, yes. Notice I could put a free body diagram up here, couldn't I? Up at the very top. But I could put it anyway. But what does this gain me? This is talking about the normal force up here. I'm not asking for the normal force yet. So you wouldn't need to do that. If I ask for the normal force, the force the ceiling is pulling back, then you would. Does that make sense? Okay. So, so if I look at how do I simplify, so we're going to get rid of that guy. So how do I simplify this guy? This one was number 1. This one's going to be number 2. That's okay. FBD 2, FBD 1, right? So we're going to draw a circle, and we're going to draw, and we're going to label it T, label this T, and then F of G. Now, in these problems, 2 things you will assume unless I tell you differently. The one thing you're going to assume is everything's static, meaning it's not moving, and 2, anything that I don't give you a mass for or a weight of, you can assume is massless or weightless. Okay? So in this case, I don't talk about the mass of the pulley, so we assume it's negligible or weightless. Does that make sense?
So doesn't FG not matter?
It does because FG is from the box. The box is pulling on the weight. You see what I'm saying? You could do a free body diagram of the box and then do 2 more force things, but if you can see that jump, you're welcome to do that. Yes, ma'am.
Do you add the box or the force of the box in a different way, or is it included in the force of gravity?
The force, okay, what's another word for the force of gravity?
Weight.
Okay, right? right, okay. So the force of gravity is the weight, which is the weight of the box, right? So in this case, I sum my forces. Why am I summing them in the y direction?
Because they're in the y direction.
Beautiful. Is there any x direction motion right now? No. Okay. Some of the forces in the y. If I assume that everything is static, meaning that everything's not moving, then the sum of the forces is going to equal. But it's going to equal ultimately the value 0, right? And then go ahead.
T plus T plus FG.
Equals 0, right? Now look, is this T the same as that T? Yes, because it's the same rope. The T throughout the rope is the same.
But you still add those T's.
Yeah, because you've got 2 forces pulling up. Okay? And that's exactly why I do this construct. So if you label it, and remember, you're putting a force for every physical object coming out of your boundary box. Do you guys see that? I have an object, which is the rope. I have another object, which is the other side of the rope. I have an object, which is metal bracket, which is being pulled down by the weight. Does that make sense? Okay. Okay, so now this is going to simplify so that now what? F of G is going to equal the opposite of 2T, right? Okay. All right, and so, but what's the value of FG? What's the weight of the box?
Negative.
Okay, how'd you get that?
Well, FG plus mass times acceleration.
Okay, when you guys do this on an exam or other thing, you've got to do this. Mass times acceleration equals 10 kilograms times what? Negative 10 what? Squared. That's going to give me a force of gravity or its weight of what? Negative 100 newtons. So that means negative 100 newtons equals negative 2 times T. Right? So T equals 50 newtons. Does that make sense? That means that my force, okay, is equal to, if it's, in this case, it's negative 50 T, but I switch it so now 15, the force up is 50 newtons. You follow that?
So on each side, it's 50. Like each tension side?
Yeah, because the tension itself is 50, so no matter where you see tension, it's 50 because you've calculated from that.
Yeah.
Do you see that?
Yeah.
So now, in this case, so in the previous case, how much did the guy have to pull If it was 100 Newton mass, 100 Newton weight, how much did he have to pull to keep that up in the previous example? 100 newtons. In this case, where I hang the weight from the pulley, how much is he having to pull up?
Only half.
Only half. Because of what you said at the very beginning, Hannah. What was the very beginning thing you said? At the very beginning, okay, so in this case, he's pulling, he only has to pull half the weight, whereas in the original case, he had to pull the full weight, right? But you said something at the very beginning. Yeah, the ceiling is holding the other half. You see?
So the only reason why I think it's positive is because it's going up, right?
Yes. You're going to get the directions from your free body diagram. If you do your free body diagram correctly, all the directions will be there for you. Okay. Does that make sense? So conceptually, the guy is pulling up, but so is the ceiling. The ceiling is as if it was another guy holding it up. Right? I know, Ashley, you're a little lost. Are you there? A little bit. Okay. I have the YouTube video on from yesterday. Go look at it this afternoon tonight, and then re-look at this one again, okay? And that, I think, should get you caught back up. All right. All right, does that make sense? Yes? Okay. All right. I think... that's not really hard, is it? Huh? I'm giving you guys, remember, I'm giving you guys a problem set tomorrow, okay, which you can all work together on, but you do your own work, right? I'm sorry? Ideally, yes. I want you to finish it by the end of class, okay? So you got to work together on it, all right? But I want you to, your own individual work, but you can work together. That'll be a quiz grade, okay? I don't know. Yeah. I'm gonna throw a couple problems down, okay? Like these, okay? Yeah. And then some of them may be challenging, right? They can make you think. And then there'll be an exam next week.
You know what day?
I don't know. When is my test day? It was Friday, but it might be Wednesday. I'll find whatever my test day is. I'll find out.
Well, if your test is Monday, we have not put it on.
If the test is Monday, I will not put it Monday. It'll be no earlier than. We don't have school Monday.
No, Easter Monday.
Easter.
And we
What
don't
then?
have school next Friday.
Next Friday?
Oh, the Friday after that.
Whoa.
We don't have school this Friday.
We don't have school. We don't have school Friday this Friday.
No.
What's this Friday?
Good Friday. And we don't have school next Friday. We shouldn't have told him. What's next Friday?
We don't have school Friday or Monday.
We have school Monday. It's not. It's Monday of next week. What's next Friday? It's not. It's Monday. It's not.
So Friday, Monday.
We don't have school this Friday. We don't have school Monday. We have school Friday. We have school. Oh, Friday. And then. So you're saying we don't have school Friday?
Next Friday.
And then.
Why don't we have school Friday? All right. Okay, let's move along. This is more complex than physics. Okay, let's move on. Okay, let's do one more problem. Can I erase this, guys? Guys, I have an answer.
I just don't know how you're supposed to know what
Tara brings up a really good question. Okay, how do you know what to put the free body diagram around? Okay, let's do this. Let me do an example to show you what you're supposed to and what you're not supposed to. Okay, all right. Can I erase this? All right. Let me add another layer. Come to this. Let's do this example. Okay. Let's do this one. If I've got a ceiling again, let me see the ceiling, and I have this and this, okay, and let's say I have, this here. Let's say I have this here. Okay? Let's say I have this here. All right? No, let's not do that. Let's not do that. All right, give me you know me, Tara. You know you have to like wait like 3 seconds after I do something before I have like rights to change what I'm doing. No, I don't. Okay. I reserve the right to change my diagram at any point in time. Okay. Let me do. Trying to think of a really good example of this. Okay. All right. So Tara, let's say I know the mass. I know the weight of the object. Okay. Okay. And more rather than taking notes, just look at this for a moment. Just watch when I'm having a conversation. This is just more about how do I know. Okay. Let's say I've got this here and this here, right? These are my brackets to hold up my pieces, right? In actuality, if I'm pulling up, that's not even real. I've got to actually have it attached here, right? Okay. Okay. So I could do my free body diagram around here, couldn't I? Okay. The problem though is if I did that, my free body diagram is T, 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 T. Does that help us?
Well, I know we're supposed to be around like an actual object.
Okay. Well, I'm just showing. I'm just giving you the whole point. You're saying you don't. So I'm just okay. That's fine. I'm just trying to figure out. If I did, let's say I put the free body. Let's say I did a free body diagram around here. Okay. In this case, I don't know what's coming in and what's coming out. Right? You've got to start with something that you know. Okay. So I could do the free body diagram here. I know that I'm going to get the weight and the tension. Okay? If I did the free body diagram around here, okay, this is probably a really good example, I think. So if I've got, that means I have a box, okay, and I've got my F of G, right? Then I have my tension, and then I have this upward force from the bracket. The problem with this, I only have one free body diagram. I don't know the bracket, I don't know the tension, all I know is F and G. I then have to go find another free body diagram to figure out your F and B. The real answer is it really doesn't matter. There's some ways you're going to do it. It's going to cause you more work. Some may cause you less. In general, for the problems that we're going to talk about in class, I would draw the free body diagram. I'll use a different color so we can clearly see what I'm talking about. Around the object, allowing the things that come out of the object to come out of that box. So we'll do this, like that. And you might even do this, but you don't have to do this one now because you know that the tension in the rope is equal to the what? You know that. You know the tension, the weight is in actuality. You know the tension of the rope is actually equal to the weight. Okay. So, but you see what I'm saying. So then you're going to draw everything physically that comes out of that. Does that help? It is. There's no real great answer, and I apologize for that. It's a little bit of experience, but you really can't go wrong, especially if you work your way backwards. Okay. All right. Everyone with me? Yes. Okay. We're gonna do. Let's do because I didn't get the friction in the last class. Let's do one more problem here. Okay.
I would be ahead of them.
Huh? You are ahead of them, sort of. But we did a different problem in that class. So let's do this. Let's do this. Let's do. right? We haven't talked about friction yet. Okay. All right. Okay. So this is actually, it looks complex, but it really is not. I promise you it's not as complex as it looks. Does it look complex?
Yes.
Okay. It's not complex. Okay. So we've got the two big things we have that are different. One, the weight is pulling down, but two, but one, the weight is pulling down and the guy is pulling horizontally, right? Okay. Does it really matter to a certain extent? Does it really matter? Okay. The other thing is we have these two pulley systems. Let's describe what's going on here. So I've got two pulleys hooked together by a piece of metal frame, and the weight is hanging from the metal frame, or the weightless metal frame. Okay. So that the total weight is pulling straight down of that weight. All right. Tara J. Where would I draw a free body diagram?
What's the weight?
We'll deal with I'll give you a value in a minute. Okay, so Tara, what was the first thing you said? The what? All the way around the three circles? Okay. Oh, individual. So you're saying put it like here, around the pulley, and you're saying around here? Okay. The problem with this, and I don't. The problem with this is that if I did this, okay, then my weight, the one thing that I know, never comes out of that box. You follow me? So you can't, you know the force is coming out horizontally, but you don't have anything coming out vertically. Yeah, you can do them together, exactly. You guys see that? So you can do the two circles like this. Do you follow what I'm doing there? Everyone with me? Do you see why I put the boundary layer for the free body diagram around both pulleys? Yeah. Because now I have two wires coming out and one weight coming out. Yes, ma'am.
Can't you not split the weight between the two pulleys?
You can. You could draw it like this too. If this helps you, you're welcome to draw this. Does that make sense? Because then the weight comes down, right? Either way of those will be the same. Okay? Does that make sense? So I've got one, I've got two. What do I know? Shh. What's the force inside the rope over here? What do we call that? Tension. So let's call that T, and that's going to be here. What's the tension in this side of the rope over here? T. What's the tension in the rope here? T. So how much must he be pulling?
T.
No, he must be pulling T. If you need to do the free body diagram like Ray suggested, here's his hand, here is his force of the man, and here is tension. So if his hand is not moving, then the force of the man pulling must be equal to tension. Does that make sense? Yeah. Okay. So that would be number 3 if I had to call it. You can do it, you don't have to do it. Yes, ma'am. Okay. Let's do free body diagram 2. Free body diagram 2. Let's draw that. What object do I use? What kind of shape do I use?
A circle.
Circle. Let's use a circle. You don't have to, but hey. Okay, what are my forces coming out of? What are my forces coming out of the
rope?
The rope going which direction?
Down and to the right.
I've got one going down, and Grace, you said to the
I said to the right.
And she said two. So what is the force? What do we label these? What force label?
Do you have X force now?
Oh, I do. Okay. Wait. Are these the only two forces I have?
Yes.
No, Tara Jane. I've got a force going up. Okay, so let's call this the force of the bracket. I'm going to call it the force of the bracket. Well, a normal force is a reactionary force. So the ceiling would have a normal force to the bracket pull. But right now I have a bracket pull up. Okay. FBD3. FBD3. No, 1, 2. Oh, I'm sorry. Excuse me. You're right. So it's FBD1. Excuse me. So what's the free body diagram 1 shape? Your rectangle if you want. Sure. Okay. What forces are coming out of this free body diagram? Yes, there are 2 ups. Okay. And then I have what? One force of gravity down. Huh? Okay. F and G. Okay. So now that I've got that, let's do some analysis. I've got my, and let's assume that the weight is equal to 100 newtons, or negative 100 newtons, right? Okay. So do I know, let's do our equation. So in this case, it said sum of the forces for free body diagram 3, sum of the forces in which direction? X, right? Because it's only X. What if my hand is not moving? What's the sum of the forces going to equal? 0, right? And what does that equation equal to? T plus Fm. Good. What about the next one? Let's go to free body diagram 1. Let's skip the second one for a second. Let's go to free body diagram 1. Sum of the forces in the what direction, guys? In the Y. And what's that going to equal? 0, because we assume it's not moving. So therefore, what do I have? T plus Fg. Okay? Now, for the middle one, what do I need to do? Beautiful. 2 equations. Sum of the forces in the X, right? If it's not moving, what is the sum of the forces in the X equal? 0. And then I equal, what do I equal? T plus what? Well, here's the deal. There's a missing force that we didn't have in here. There's a force reaction of the bracket. Let's call it bracket Y, and bracket X.
Wait, that's a little bit much.
Okay. Let me ask you a question. This is a bracket, right? Let's assume I'm holding this pulley, okay? Hold the pulley, right? My hand is the bracket. It's a metal, okay? If I'm pulling this way, what's going to stop the pulley from moving that direction?
Your force.
My hand, right?
Yes.
What's stopping the pulley from going down? My hand is stopping from going down. My hand is the bracket. So my hand is having to deal with horizontal and vertical forces.
So why aren't we doing that with everyone?
Because we've been dealing with everything purely in one direction. In every case, like the box, this is sitting purely in one direction on the table. Right? We've been pulling purely vertically on the ceiling. Okay? But in this case, you've got, now this will be the most complicated you ever see, I promise. Okay? And so, in this case, there's a bracket that has to support the vertical, but there's also one supporting the horizontal, so plus FBX. Do you guys see that? Okay? Then I get to sum of the forces in the Y. That's equaling 0. So what do I have? FBY plus T. You guys see that? Do you see why I call it FBY and FB? There is no F and there's no normal force. Normal force is a reaction to like at a floor or ceiling. Technically, there's a normal force there, but let's not go down when you get down to that level. So now I've got 3 equations. Okay, what's the only value that I know? That's what I said. We have 4 equations. We have 4 equations. Forcer, yes. So what's the only value that I know? The weight. Where is that, or f of, which is also our f of g, right? So which equation should I start with? FBD1, because it's the only one that had. Yeah. Okay. I believe you. I believe you. Shh. So 0 equals 2 times t minus 100 newtons. You're right. So t equals 50 newtons.
Please shush.
Okay. So t equals 50 newtons, doesn't it? Yeah? 0 equals 2t minus 100 newtons. T equals 50 newtons. Right? Yub. Okay. Yes, but 2t plus f of g, 2t plus the weight equals 0. You follow this, Morgan? Right. Okay, now, I can then use, since I know t, is the t in these cases all the same? Yeah. So let's see. So 0 equals, in this case, here's the important part, for FBD3, the top one, the x direction, what? Yeah, t is what? Negative, because it's going to the left. So it's negative 15 newtons plus Fm equals 0. So Fm equals a positive 50 newtons. So he's pulling with the tension of 50 newtons to the right. Again, the sign only tells you direction. Okay? So in terms of the x equation here, okay, I have 0 equals t plus fbx. Now, in the x direction, is t positive or negative? In this x direction? A positive. So it's going to be 0 equals 50 newtons plus a negative, plus fbx. Right, so fbx equal to negative 50 newtons. This is why I don't put the negative sign up there, Terry, because I'll end up having to do a double negative. That's why I leave it as a positive, right? And then I say, okay, on the next one, I say, okay, t is in the y, t is what? Negative or positive? In the vertical? Negative. So 0 equals fby minus 50 newtons. Therefore, fby equals 50 newtons. So the bracket has to support 50 newtons from the left and vertically, horizontally and vertically, individually. But these are component vectors. These are component vectors. And actually, that means it's pulling. If it's pulling up, if the bracket's pulling up and to the left, that really means that there's a final velocity vector this direction. Okay, that you can calculate, that I'm not going to make you calculate. All right? Okay. We got 4 minutes. I want to talk friction for a moment. Okay? I want to get you an intro to friction. Okay. Ready? Okay. What do you guys think friction is? Tell me what you think friction is. That is a result of friction.
It's like two running together.
Okay. All right. Friction is a force. Friction is a force. And it's a force that happens between two objects. I have my iPhone with a nice clear plastic cover. I have a nice smooth tabletop. I put together, they're pretty smooth, aren't they? But do I still have friction? Yeah, because it's not sliding off the table when I move it, okay? So when I look at two objects that are pretty smooth, my iPhone and the table, and when I zoom in on this object, or this spot, okay, with a microscope, and look at it through a microscope, what I see is a bunch of this.
So technically aren't straight edges.
Technically, they're not straight edges. They're not smooth. They really are broken up. If you zoom in close enough. And if I zoom in again here, okay, and I look yet again at one peak and valley, it actually looks like this. I'm just giving you this example, right? So as I'm trying to move these things by each other, I have these peaks and valleys pushing back on us. And we'll talk tomorrow a little bit more. Actually, we'll talk on, we don't have school Friday?
No.
Oh my God. Okay, we'll do some more friction next week. All right. See you guys.